Chapter 6 focuses on marginal and conditional distributions, which is another way of saying if we have a set of data and we break it apart into margins, like say for example splitting data between men and women, analyzing those separately, would be referred to as a marginal distribution. Now, marginal distributions can be a little bit misleading, and so I wanted to look at what's a better way to statistically analyze them. And a conditional distribution is fairly similar. It's just instead of looking at the data as a whole, we're looking at certain points based on certain conditions. So actually, what I wanted to do in our lecture notes is look through example 6.4 from our textbook, because I thought it was a really strong way of a really strong example of a marginal distribution, because sometimes marginal distributions can be misleading when we don't break them apart, and also it looks at how lurking variables can be at play in certain things as well. So the data that's provided in this example tells us the statistics based on how well do accident victims survive when they're transported to the hospital via helicopter versus via ambulance or by road, however you want to say it. But let's just say that some patients are taken to the hospital in helicopters, certain patients are taken to the hospital in an ambulance, and we basically have their data on how well they survive. So number 10, and by looking at a marginal distribution such as this, we see the raw numbers, but we don't really get a sense for how well things are being, how well say for example, how safe it is or how well do patients survive under these methods without looking at the percentages. So a key with marginal and conditional distributions is we usually want to look at percentages, not just numbers. So that's what number 10 tells us to do. Calculate the percent of victims who died. So this is a typo, obviously. I don't need two of those. Percent of victims who died or survived when transported by helicopter or by road. So basically, notice that we're provided with the total. You wouldn't always necessarily have the total for a marginal distribution, but if you don't, you can obviously always add them up to find the total. And this is assuming we know all the data. Certain marginal distributions would be conditional and not have the full picture. But anyways, let's go ahead and see. Well, we could check the percent who died. Well, that would be 64 out of 200. This would be by helicopter. Percent died by helicopter. And so 64 out of 200 would be 32%, meaning that around a third of the patients who were transported by helicopter died. And of course, we could also figure out the percentage who survived in terms of a survivability rate, but that would just be exactly the opposite since we have the total. It would be the inverse percentage, which would be 68% survived instead. Now we could do the same thing for ambulance or by road, but let's see what percent died when taking an ambulance instead. And here there's a different total. We had 260 died. It kind of seems like there's a lot more that died, but when taking it with respect to the total, it's more meaningful because this will give us a percentage, like a rate of how many died based on the total. So 260 out of 1,100. And this would give us 23, approximately 23.6% died by ambulance, and the rest, 840 divided by 1,100, survived. So roughly we have a survival rate of 76.4%. And of course, a higher survival rate is better because we want more people to live. So we can kind of now have a grounds for comparison between a helicopter and an ambulance. And this is a little bit interesting because what our conclusion might be in this case as well, it seems like it's safer to take an ambulance than to take a helicopter to the hospital because you're more likely to survive on a percentage basis. But this is a dangerous assumption to make because taking an ambulance and taking a helicopter might not be, you're not going to take a helicopter in the same situations that you would take an ambulance to the hospital. So this data, while we're comparing it, the question is, should we be comparing it? Maybe, maybe not. And again, this is where lurking variables could come into play. So what's actually interesting in this case is if we split up the data into two categorical variables, basically how serious were those accidents to where they warranted taking a helicopter versus an ambulance? Because if you think about it, common sense would be that helicopters are usually for way more emergent cases, like for people who are in much more critical danger, like say an ambulance can't get to them, or they would be in an unsafe environment or whatever. So actually, if we look at the split of this data, we see here it's split into categories where how many of those were in serious accidents and how many of those were in less serious accidents. So of those 200 helicopter patients, 100 of them were in serious accidents and 100 of them weren't really in that serious of an accident. And another question you might have is, how do you determine what's a serious accident and what's a non-serious accident? But again, we'll just pretend that this data is just created to help illustrate a point, but we'll go along with it and just say there's probably some way of determining what is serious and what is not. And then for road, we only have 100 serious accidents which are deemed serious, but 1,000 which are deemed less serious. And if we did the same thing, we could analyze, well, what are the percentages when we break them down based on category? So we can see that in the serious accidents, 48 out of 100. So let's go ahead and kind of calculate the percentages in the same way. So here's the serious category. The death rate by helicopter would be 48 out of 100 died. So 48% of our patients died on the way to the hospital when taking a helicopter. But if we look at the road, it's actually it's way more extreme. 60 out of 100 died on the way by ambulance. And one of the obvious, reasons why this could happen is, well, helicopters are quite a bit faster than ambulances. Usually they don't have to take streets. They don't have to stop at lights. Well, ambulances don't either, but helicopters could travel faster, be more direct, have access to more resources. I mean, there's a lot of other variables that could be at play as well, but just based on looking at these statistics, actually the helicopter did much better at getting the patients to the hospital alive in serious accidents. Now, what about non-serious accidents? So only 16 out of 100, let's go ahead again, death rate for the helicopter, only 16 out of 100 died. So 16% died on their way to the hospital for less serious accidents in the helicopter, not as bad. And if we look at the road accidents, it was actually 200 out of 1,000, which would be 20%. So the death rate of the ambulance was 20%. And notice it's actually higher yet again. The helicopter actually did better at getting people to the hospital alive, even in non-serious accidents as opposed to accidents themselves. And so this can be quite a strange happening, because when we lumped all the data together in the first table, we actually saw that the death rate was worse for the helicopter than it was for the ambulance. But once we separate it apart, it's actually better in both categories. And this can seem very strange. Like, how did this happen? How was it worse when all the data was together, and when it was separated, they were both? It seems like it paints a completely different picture. And this is often what's referred to as Simpson's paradox, where when data is clumped together, it can be very misleading. But when it's separated, it gives us a more clear picture of what's actually happening. And statistics, as we talked about in class, can be used in a misleading way, like using a regression line that has an R squared of 0.03, like the California building code has for parking lots and fast food restaurants. Statistics can be used very poorly and or also in a very good way as well. And it's up to us to really understand what is good use of statistics and what is misleading statistics as well. Anyways, not to get off on that tangent, but so the last thing I want to talk about is, well, why did this happen? How is this so different? But really the key difference was in the sheer number of less serious accidents by ambulance. When lumped together, it created a ton more road accidents. And so the percentage was 260 out of 1,100, a lower total percentage, because this stat was grossly inflating the overall death rate of ambulances, because there's way more ambulances that respond to less serious accidents than helicopters. And the sheer number kind of pushed the average death rate closer to that because there were so many more instances. So it made it seem like the death rate for ambulances was lower than helicopters, because these two, there was a more proportionate amount of calls between serious and less serious injuries. So notice that the death rate for helicopters was higher than that of ambulances, just because of the sheer number of less serious accidents. And obviously, the death rate combined, when we're not looking at it marginally, when we're looking at the combined data, was much lower for non-serious injuries than it was for serious injuries. So it makes sense that ambulances would have a lower death rate overall, because they respond to way more non-life-threatening calls.